An Aston Martin V12 Vantage sports car has a lateral acceleration of 0.97 g. This is the maximum centripetal acceleration the car can sustain without skidding out of a curved path. The car is traveling at a constant 40 meters per second on level ground. First of all, what is the radius of the tightest unbanked curve that this car can negotiate? Conceptually here, what we have is uniform circular motion, and so what you might want to do is remember that what that involves is, for one thing, a circle of some radius, we can call it capital R, and it also involves an object that is moving around at constant speed on that circle. So there's some speed v. V is constant. And the important thing about uniform circular motion is that there is always an acceleration pointing towards the center of the circle, the so-called centripetal acceleration. And the centripetal acceleration is simply related to the speed and the radius of the circle, given by v squared over r. So in this problem, what is the radius of the tightest unbanked curve it can negotiate? We're going to use this equation, a equals v squared over r. We also need to realize that the acceleration is given by this value of 0.97 g. In other words, almost 1 g of acceleration. What does that mean? That means the acceleration is literally 0.97 times the value of g on Earth being 9.8 meters per second squared. That tells us the acceleration is 9.5 meters per second squared, so close to g, but not quite. Since we want to know what the radius is, the idea is that we'll use this as the acceleration. This is the speed. And if we use our relationship between acceleration, speed, and radius, we can figure out what the radius is. A little bit of algebra, multiplying both sides by r and dividing by a, will tell you that the radius that obeys this formula is given by v squared over a. Now, if r is any bigger than this value, then the acceleration would be too much. Sorry, if r is any smaller than this value, then the acceleration would be too much, and the car would not be able to stay on the road. So let's put in the values that we have. 40 meters per second squared, the acceleration of 9.5 meters per second, and we determine, writing this out, 168.4 meters would be the radius. Now, this isn't the final answer that I'm going to record. I'm going to round this to 2 sig figs, and so I'll write this as 170 meters. It's important that we keep around that unrounded value as we work through the rest of the problem. That was part A. In part B, at the speed that we just are given, 40 meters per second, how much time would be needed for the car to go around the circle of radius r one time? It's important to realize here, if you're going around a circle at a constant rate, then the speed is simply related to the distance and the time in this way. Distance over time is the speed. The distance is the circumference of the circle. That's one time around. How much time does it take? Let's call that capital T, also known as the period. If we were going to figure out what the period is, that is to say the amount of time it takes to go around one time, then I can relate v 2 pi and r to t by doing a little bit of algebra. Multiply both sides by t and divide by v, and you'll find that the period would have to be equal to 2 pi r over the speed. We're ready to plug in the numbers we have, 2 pi and the radius, but here's where I'll use 168.4 meters as the intermediate value to do the calculation. The speed is 40 meters per second, and what you'll discover is that this is 26.45 seconds, which we'll round to 26 seconds. Importantly, if you used r was equal to 170 meters, then the period you would get would turn out to be 26.7, which would round to 27 seconds. And this is a less reliable number. It's very important to use the unrounded numbers when you do your calculation so that you get a reliable number in the end.